Thank you for joining in and being a part of this evening. This is Shruti Khurana on behalf of TCS ION. I welcome you all to this masterclass where we'll talk about masterclass on Sigma Delta ADC mixed signal design perspective. In today's rapidly evolving tech ecosystem, the demand for high performance, energy efficient, and compact devices is fueling innovation across industries. At the core of this transformation is VLSI, very large scale integration, driving advanced system on chip SoC design. This exclusive masterclass on Sigma Delta ADC mixed signal design perspective in collaboration with IIT Hyderabad will walk you through the essential of modern mixed. This exclusive masterclass will you will learn explore how Sigma Delta ADC are architected to deliver exceptional resolution, noise shaping, and power efficiency, making them integral to next generation applications. Key highlights of the session is the fundamental of signal delta, ADC and analog signal IC design, architecture and working of Sigma Delta ADC, oversampling, noise shaping, and digital filtering concepts, essential building blocks, modulator, integrators, quantizer, and decimation filters. Design traits of resolution versus speed, power versus accuracy, loop stability versus complexity, real-world applications in audio system, biomedical devices, communication systems, and IoT. Whether you are a beginner stepping into the world of mixed signal design or an enthusiast aiming to strengthen your foundation, this session will equip you with practical insights and real-world perspectives. We are delighted to welcome Ashudeb sir and Aditya, who are from the IIT Hyderabad. And with extensive expertise in VLSI chip design, they will walk you through the fundamentals and dive deep into the world of Sigma Delta ADC mixed signal design perspective, helping you to connect theoretical concepts with real-world applications. So let me introduce them first. Professor Ashudeb Dutta is a professor in the Department of Electrical Engineering at Indian Institute of Technology, Hyderabad. His area of research includes analog and radio frequency IC design, whereas Aditya is a final year student in Electrical Engineering Department of IIT Hyderabad. He is interested in analog and mixed signal circuit design. A very warm welcome. So, sir, I would like to take a first question that in the electronic and semiconductor space, VLSI has become a key area of growth. Yes. Could you share what kind of career opportunities and job roles students can explore in VLSI in areas like analog IC design, mixed signal design, such as Sigma Delta ADC, or what are highly relevant today?
So I remember in the last webinar, I explaining that anything you want to see, which is analog, and finally you have to convert to digital. So any activity, whatever the you have seen in camera, or you have seen audio, or if you have seen that RF, everything there is a data converter associated on that. So it will have to be digitized the data, and finally that will be processed by your multiple kind of processor, like Snapdragon processor or Intel Core processor, whatever they are. So ADC is one of the critical part on that. And analog and mixed signal design aspect, you see, you know very good of the analog as well as digital design in a custom form or in the porting form, that will be called mixed signal. So that you have to do analog, which is frequency is variable, whereas digital means frequency may be not variable, but it will be something like a 10 steps. So there will be two different environment, and there is enough job opportunity in the company like TI, ADI, all of the big company. They have this vertical on the analog and digital together called mixed signal. So you have a knowledge of digital is required as well as knowledge of analog is required. And overall, this digital design knowledge also you can pursue for the other digital company like AMD, Qualcomm, and those are the big giant in the digital. So this experience, if you go through, they also will be happy to take you in the digital domain also.
Great, sir. You have clearly highlighted how VLSI chip design, through its seamless integration of digital fundamental and analog circuits, continue to power modern electronics. It's equally inspiring to see how specialized areas like Sigma Delta ADC and mixed signal designs are becoming highly significant, opening new paths not just for core electronics students but also for learners across diverse disciplines. So, with that encouraging perspective, let's now explore this subject in greater depth. So, over to
And
you, Aditya.
And I one more points I'm
Uh,
telling you because to comprehensive of the last presentation where they have given to the pipeline ADC, which primarily objective is to that speed to increase, resolution also moderate, but still good on that. So there is a different design challenge which is covered, and this case also will be covered different design challenge, which Aditya will cover the Sigma Delta ADC and more of that. I think one important point here maybe will be two session will be in the September end will give to the students one-to-one direct interaction, not in a chat box. We are trying so that they have any QA, we can able to answer them directly by face to face in the webinar platform. Okay.
yes, sir. Definitely, definitely. Hope students noted these points. So,
Yes.
these are actually a very important points.
So Aditya,
Thank you.
please take up that one. Aditya.
Uh, thank you so much, sir.
Thank you.
So, Aditya, now I'll hand over the session to you. Please continue with your presentation.
Why we are going for discrete time delta sigma modulator ADCs? That's the first thing. We already have other kinds of ADCs, other kinds of architectures. Issue with any like circuit you're building on silicon is that mismatch, especially for something like a analog to digital converter. If you want to build like a 16-bit, the constraints on mismatch are very tough. So even like 8-bit, like 1/64th of the value, you can't cross over or have a mismatch greater than that. For 16-bit, it becomes like 1/64,000. So that's like percent of a percent, less than that. So you can't really extend whatever designs you already have. You can't extend a SAR to a 16-bit. You can't extend these other quite easily. So you go for a completely new architecture. Two things are changing here. ADC means analog to digital converter. So get an analog signal from anywhere, like even like a touch sensor, some audio signal, in a converting into digital bits. So we're solving this through two things. So oversampling, noise shaping. I'll explain what those are in the session. But the beauty of delta sigma modulation circuit, or like this delta sigma modulator ADC, is you can use a 3-bit ADC and a 3-bit DAC, and collectively they can work to give you a 16-bit ADC. So making a 3-bit ADC is like really easy. It's not uh, from a design perspective, from testing, it's a pretty easy thing. So even with that, you can build 16 bits. So I'll cover like how it does that. Additionally, something that we should look forward to is that if you're making any circuit, any architecture, you should have an idea about what will happen if we could go to a lower node. If we're making something at some node, like processors, they over time they go to a lower node to get better performance. Mostly in analog circuits, that's not the case. You can't go to a lower node to get higher performance. But for delta sigma ADCs, for the most part, it does work because we can go for a higher frequency. So higher frequencies allow us to get more bits out of your modulator. So this slide, you may not understand anything of like what's written here. Static current bias OTs for integrators and floating inverter amplifiers, etc. And this diagram. By the end of this session, you should be able to understand everything. And I'll mostly be explaining this. It's a journal paper by Dr. Ashwin from IIT Kanpur. So first on the concepts, then I'll cover how to design as well. So, okay. Let's say you take any sine wave you quantize it. The quantized version will look like the black line here. Or quantized, I mean the digital signal will always have some error here because there's a limited number of values that it can have. So either it can be this value or this value, the digital signal. So there will be some error in the middle, which is shown in the green here. So one thing which should be like crystal clear to you, it is essential that you understand this. You can, if you're going for a higher bit ADC, this is 4-bit, so some like what are 16 levels. If you go for a 5-bit, these levels will be closer, so this noise will be lesser. The higher the ADC, the lower the quantization noise. In a 16-bit ADC, this is supposed to be in microvolt levels. So I'll come back to that, how this quantization noise comes into play. Okay. So yeah, would anyone like to answer this question? Let's say we have a communication medium. We can just send 1 or 0 every second. You want to send a number like 0.25 in like some interval of time. Is it possible? One basic way is you convert it to some like how we represent 0.25, you can represent it as a fixed point number by just with binary weight, right? How you can represent like 7 as 111, right? So the first one represents 4, then 2, then 1. So similarly, you can go for your decimals as well. Another method is you just send 4 bits, like you send a number 4 times. Out of 4, 1 time you send 1, the rest of the time you send 0. So this is basically, instead of binary weight, this is just all the bits are equally weighted. And if you just average them out, you'll get 0.25. Now, using that method, if you want to increase the precision of the number, so let's say instead of 0.25, we want to send 0.371, let's suppose. Then we will need much more bits. Many more numbers we'll have to send, which should average out to 0.371. So we can send like 1000 bits. Out of 1000, 371 would be high or 1. The rest will be 0. If you average them out, you'll get 0.371. So if you want more precision, you need to increase the number of these bits you're sending. So it is not that for a 1-bit increase in your resolution, you need to double the number of times you're sending the bit. So through this way, can a 1-bit stream of number describe a 16-bit number? Using the method that I described, where you send either 1 or 0 and you average them out over time. Is it possible? 1-bit to 16-bit, this is even possible. You need to average out to a much larger extent in this case. And this in general is what oversampling is. That you want to send some data, your communication medium can't handle that level of resolution. So you use more number of samples and average them out. That's the first thing. Second thing is, so image decides that you have some amount of signal, but you're using only like some part of it. So the k times, that's the oversampling ratio. Second thing is noise shaping. That if you have integrators in your path, so here, because you have integrators in the path, the signal that you're sending here sees a transfer function which is equal to 1 and we construct it to be 1. And this 3-bit ADC, as we described quantization noise. So 3-bit ADC will add its own noise here. So that noise sees a transfer function which is called noise transfer function, which is basically passing through which is a low pass filter. Sorry, yeah, this is a high pass. Sorry, I'll just show it here. So this is the filter that the noise sees, the high pass filter. So the quantization noise sees this filter. The lower power of the lower frequencies gets transferred to higher frequency, but our signal, in-band signal, that doesn't get changed. So this is the noise shaping that we're doing. The filter, how do you get that? Using MATLAB. So you can calculate it by yourself as well, but if you want to build like a 100 dB ADC, 100 dB would mean like 16 bits. So doing the calculations for that and like making sure that this 7/15, 7/6, these 5, 5, 4, 3-bit ADC. So what we need to choose is the number of stages. So here there are 3 stages and one summing stage. We add all of these. So few things we need to decide. Number of integrator stages. The more stages you have, the more power it will take. Integrators are the most power consuming part here. Number of levels in quantizer. So this is a 3-bit ADC. You can go for a 4-bit ADC or even a 1-bit ADC. If you go for a 4-bit ADC, your quantization noise will be lower, so your noise shaping will be better. But building a 4-bit ADC is more complicated. That itself will take more area. So there's a compromise. So if you go for a 4-bit ADC, maybe you don't need 3 stages then. You just need 2 stages. So you need to figure out which would be the most optimum solution for your requirements. And
okay, Aditya, we have one question. The student is asking, what is ADC?
Yeah, at the start I had said it. So analog to digital converter, the short you is called AC. The analog signals, like the signal which is going into a microphone, that is analog, and it goes into a sensor. That sensor will process it, amplify it. But for a processor to handle it, like your computer processor or phone processor to handle it, it needs to be in the form of digital bits. So that conversion, especially for like audio or something, it needs to be like 16-bit or higher. The resolution needs to be pretty high. So we're discussing how to design that kind of ADC. Digital thermometer. Yes, anything which, so unless any system is like completely digital, it will have some analog to digital converter, even like 1-bit converter, like some crossing over point needs to be there to decide whether this is like what is the level of the signal. Number of levels, that was explained. Oversampling ratio. Digital thermometers would have a ADC. Oversampling ratio. So for this is the last point here before I can hand it off to you. So when we're talking about the overall ADC, we're doing the oversampling. So how many samples we're going to average out to get our result? So generally people go for like 30 to 64 in this kind of case. You can go for higher as well. You can go for like 4,000 or something. The issue is that if you want a bandwidth of let's say 50 kilo and you're using a oversampling ratio of like 1,000, then it needs to run at 50 mega or even higher. So that is where the issue is. If you go for like such a high modulator frequency, your power consumption will be very high. So in that case, it may be better to use better integrators or like a higher bit ADC. And we generally over design it by 10 dB because after you design it in a circuit in silicon, its performance will go down. Not an idea it is.
Okay, great. So one of the students is also asking one question based on this. Does we have a ADC in the digital thermometer?
Yes, we would have it in a thermometer as well.
Great, great.
So now that at this point we should have the coefficients. So we have something like this. We know we have the integrators here, and what should be the ratio here, and how many bits of ADC need. So next step would be we implement it in Cadence. So that's the EDA software we use here. You can use other software as well, but you need to make it in circuit. Not a real circuit. You don't need to make it using transistors and all amplifiers directly, but ideal integrators, which are usually present in some libraries, they usually contain. Switch is also ideal. Quantizer ideal. So just make the entire thing, but ideal. That's the second step. So it will look something like this. So here it's an amplifier, and if you arrange it, if you keep a cap here, you have a lot of switches here to either reset it or to use it as an amplifier. So this circuit you need to make using all ideal components and then see what is the SNDR you're getting, signal noise and distortion ratio. So that you should be able to see, like if you designed it for 110, let's say you want to design 100 dB ADC, you should design it for 110 on MATLAB. Here at this point, you should see like at least 105, 108, something. If you're not seeing that, you need to figure out why it's not working here. Although it is working here in MATLAB. So there could be some issue with the connections. There could be some issue with your circuit itself, because that's the only change which is present here. Then once that is done, you need to change it to real caps. So all these caps, you can keep them as ideal at first, but at this point you need to keep them as real. The thing with real caps is they take up a huge amount of area. So you need to be careful about it. In our design, so for context, the entire area of the transistors versus the area of the capacitors. The area of the capacitors were like nearly double, or like slightly more than double of the area of the transistors. So it is essential that you know what capacitors are there, try to minimize them as much as possible. And once you have completed the third part, so still ideal integrators and DAC, but the caps are real, so that you have some idea about what kind of size, what kind of area you're dealing with. Yeah. And how to decide the caps. The input cap, this 8CU here. So at the start, all the charge will be stored here. This size is determined by the KT by C noise. So that KT by C noise is the noise floor of your circuit, because this at the input. That noise floor should be lower than your 100 dB. Otherwise, it can't work. If the cap is too small, just the noise due to the cap will be higher than 100 dB. Or like whatever signal level is, it should be below 100 dB compared to that. If it's not, this capacitor noise itself will dominate it. And you can't make a ADC in that case. So this cap itself has huge constraints placed on it because of that KT by C noise spec. Then I'd replace the ideal amplifiers with real amplifiers. So here I'll briefly go over what amplifiers we're dealing with. So two factors. bandwidth and distortion. So because we're driving caps here, can this amplifier drive the cap to enough voltage in enough time? It is not necessary that it settles to that voltage, but it should be that it settles to a close enough value. That bandwidth you can calculate using some. So whatever your modulator frequency is at least it should settle to that value. Generally, that is how we look at it. People usually over-design it by like 10x or something. So if your modulator runs at 5 mega, you design it with a bandwidth of 50 mega, something like that. That's what the bandwidth here is. Second, distortion. Any real amplifier you have, it will have some distortion. It will have some non-ideality. You send in a sine wave, you don't send out exact sine wave. It will have some distortion. It could be very low, but you should know how low it is. So basically the question you're asking is this amplifier linear enough in the output range it would operate in? Also, the output range is pretty important. If you want to use an amplifier with an output swing of like 1 millivolt versus 1 volt, the distortion would be completely different in these two cases. So you need to be sure that what kind of output swing is this amplifier going to see when it's being used as an integrator. So, and these two should be tested independent of the ADC. Okay. So, bandwidth I've covered. You go for 10x of the modulator. You can go for like a tougher, a tighter constraint. That is usually like an easy answer. The third harmonic would usually be the strongest and the most powerful distortion in your output. You can check it in the spectrum of your output of your amplifier. So how do you check it? You just use it as a unity gain buffer. It doesn't matter if it's a continuous time amplifier like your normal OTA or a discrete time, which if I get time to cover, I'll cover it in the end. And check output spectrum at the required output swing. That's the important point, required. So we have this entire modulator. For any given input, how much is this going to swing, this node? How much is this node going to swing? How much is this node going to swing? That is what determines this output swing. So what you can do is you deliberately change these parameters, like here 7 by 15 and 5 here. The reason it's done this way instead of doing just 5 here is that then the swing here would be much higher. So the distortion would be higher. So you just, instead of doing 7 by 3 here, we do 7 by 15 and do the 5 later on. So these kinds of some tricks you can use. And additionally, you can scale down everything by some factor. Output is supposed to go from 0 to 1.8. You scale it down by 1/3. It should go from like 600 to 1.2. So that this again is the amplifier here. So that doesn't have to work that hard. Its third harmonic won't be that high. So those kinds of tricks you can use. About the spec, how do you decide if the third harmonic is good enough? The first stage is the most critical stage. Other things are really like they don't matter that much. Third stage, the last stage, your summing thing. If you have a summing kind of architecture like this, this last stage will be critical. Not as critical as this. This will make or break your system. The first stage, and first stage, gain your bandwidth. You can ensure pretty easily. Like you can just use maths, calculate it out. You can just throw more current at it. You can get more bandwidth. Third harmonic is pretty critical. Here, the spec that I've seen people use is third harmonic power. Like how low the third harmonic is compared to your main signal. This you write it as HD3, whatever it could be, like some 50 dB or something. And gain of the first stage. So the amplifier gain here. So higher the gain, lower the offset, right? In case you've seen for like unity gain buffers. If you have a higher gain, the error between your plus and minus and like how correct your output is, that will become more and more accurate as your gain increases if you're using it in a negative feedback. So multiplication of that should be less than your SNDR spec. So this, let's say, is 50 dB, gain is 50 dB. We are reaching just 100 dB. So here, this lesser sign, it's because we generally take HD3 as negative. So that's why. You want your third harmonic to be as low as possible, gain to be as high as possible, so that you reach like 110 dB or something here. Then change amplifier structure. So you can use a different kind of amplifier, or you can change the cascode devices, etc. That's one of the steps you can take. A better option, or like if it is possible, you can change the loop filter. Like here, the 5 is shifted later, so the swing is not required that much. They need to carry a lot of current, so these ones need to be large. Later ones can be smaller, but you need to make sure that the switches are working correctly. If they're not, that is like a pretty, it's like a very basic thing, but it can cause significant distortion, significant issues in your circuit, just because the amplifier is working correctly, but the switches are not strong enough or like big enough to carry the required current. Additionally, when you have all the switches, the input switch is especially important. So this switch, because whatever value gets stored in this capacitor, if that value itself has some error, some offset in it, or it is not charged completely, that is what this modulator is going to process. So if the first switch itself is not good, can't really get any performance out of it. So the first switch is actually, like, if you check the lecture 4 and 5 in this playlist that I've mentioned here, it's like a 1-hour lecture by itself, the gate bootstrap switch, and how do you design it, how do you size it, and all this, how do you connect the body of the device, etc. It's a like pretty involved topic by itself. So effectively what you have here is you just have a PMOS switch, and if you just use, let's say, a PMOS switch with a 1.8 volt, everything is 1.8 volt, 1.8 volt at the gate, and you want to try to pass any signal through it. If your input itself is 1.8, it can't pass it through, right? It will drop a huge amount of voltage, nearly equal to the VTH, if you want to pass through 1.8. So one option you can do is you keep a higher voltage at the gate. You use a like 3.3 volt or 5 volt device for a pass transistor, and you keep your gate at, let's say, 3.6 or something, always. The issue with that is, let's say you give an input of 0, let's say you give an input of 1.8. In both of those cases, the resistance seen would be different, and that would introduce distortion. So to overcome that, we have this whole complicated circuit. So what you do is you charge a capacitor to 1.8 volts, and you keep that capacitor between your input and the gate. So you're effectively keeping a gate always at 1.8 volts above your input. So the resistance seen while charging your cap, that is equal in all cases. There is still some small non-linearity which is present here, which is due to the body. The body is still grounded. You can isolate this as well, but it may not really be required. It will still cause some issue with the VTH changing as your body is at ground, but your entire transistor is like jumping from 0 to 1.8 or something. But this VTH difference, it's not that critical. If you're going for like 100 dB, maybe if you're going even higher, it may be required. But I've usually not seen that this body being isolated as well. Then quantizer. If you've changed the switches as well and it's giving you SNDR above 100, then you're like nearly done at this point, because quantizer is pretty easy. If you want to make like a 3-bit, 2-bit, even 4-bit flash ADC, it's really easy. You just use a strong arm latch. Strong arm latch is a discrete time comparator. So most of the time when clock is low, this transistor is, I'll try to use a pointer here especially.
Okay, so what Aditya's covered on that, I'll be cover few basic things. What is your question was there? Suppose you have gone through class or pipeline or SAR ADC, which is there, which has a very straightforward equation, which will be followed on that. That will be dynamic range or SNR is equal to 6.02 B plus 1.76. B is the resolution rate. Suppose you want to do 8-bit, you want to do 12-bit, something like that, you can do. But SAR people have targeted 8 to 18, but not 8 to 18 because they still in the 14-bit level. They are there. They have not get it to 18 bits yet on the SAR on that. Okay. What is 18-bit meanings? 18-bit meanings is what Aditya said. It means your representation will be more accurate, basically. So why that accuracy is required? Because the question is that, sir, I'm okay by that, say, 8-bit also. Because signal shaping, suppose if you look the signal, if we just tell we go to next slide, then will we get it? Suppose this is the signal, right? If you see, this is the signal, right? On that. So signal somehow it will be quantized, right? Different quantization has been done. Right? So this quantization level, if you get a accuracy, then it is okay. I don't need to go for 16-bit or 14-bit or 18-bit. But if you look, suppose you want to accumulate the temperature of a multiple server node. Suppose server has a rack, right? You have seen your, so let's say assumption your house is there. House has a, your fan is there, 3 fan is connecting, right? Suppose there is a some temperature change is there, say 1 degree, other fellow change is 1 degree and another fellow change is 1 degree. So 3 degree is the temperature change, right? So it will be accumulately 3 degree, individual 1 degree, but accumulately 3 degree. So whenever you see that so many data center or so many computer or so many thing is there, they need one of the first thing is that suppose I want to measure a temperature, I need a very accurate, so that multiple card is there. Even they have a 0.01 degree extra, so many card will be blast that complete the that systems on that. Okay, it is not a single card, right? There's a million and million people are using the data center, like your temperature, what is there. So very accurate precision of the temperature is very important. That time your sigma delta come in the picture. So it will be very high resolution ADC is required. So suppose audio processing you are doing. So you have a lot of noise associated on that, right? You want to filter out that noise, right? So you have to be very accurate signal presentation is required. And you have to understand the noise presentation also very well. Noise means not a thermal noise, is the environmental noise. Okay. Then you can subtract that and then you get a good quality of thing. Next, you see today's date, you have a picture. Whenever you are taking camera, you are getting a very nice picture, right? But you are doing some kind of software programming or this thing on that. There is a so many pixel is coming on the picture. They have to take so many bit resolution on there. Okay, so all will be combined, right? You understand. So when you want to get a better resolution picture, you understand each of the pixel have to decode in a very minute way, very resolution way. So that's why the point of the SAR or class ADC, that will be not work because their restriction is dynamic range only 6.602D plus 1. That's mean number of resolution bit is like for 8-bit, 10-bit, whatever there, it number of level will be very low, or resolution is very low, or accuracy of the signal is very low. But one of the important point what I'm trying to say you, this kind of whenever you are telling SAR or pipeline or flash, it is a very straightforward architecture because you are getting bits. As if you know, this SAR ADC means flash ADC means this many comparator. SAR ADC means this comparator is there. After that, it will be logic, whatever logic gets, they'll give that some value based on that will be getting. So it is defined as a bit level. But sigma delta never defined as bit level. There is no bit concept on that. Basically, it's a virtual bit. That is the very beauty of that sigma delta. It's like there is no level as such. Whatever, it will be some kind of signal stream will come. You have never seen that there is a 1 level, 2 level, 3 level. But if you average that one, if you do equivalently, you find out that SNR is this much or the equivalent beat is that much. Okay. So if you look the, I have wrote what is the sigma delta level, what is the representation, completely different representation. It is no longer related to this single relationship. This is the quantizer. What he said, 3-bit quantizer, right? What is the last stage he said? There's a 3-bit, right? Then there is a OSR. OSR means oversampling ratio. Let's order of the modulator. You are using third order, second order, fourth order. We have a good book is there. I'll be, whenever you come to IIT Hyderabad, we'll be show you how this equation has been derived, how this has been get it, and then you're able to see how you can design. That's why you should come to Hyderabad. IIT Hyderabad, that's this, take the course and come to Hyderabad. See that, how will we get it? That one finally on that. Okay. So what I said, it is this B is no longer the B. Actually, this B is the last 3-bit, whatever he's telling on that. Then this is the order and this is the OSR. Now question is that what it will help? Suppose you look, why I'm telling, he said OSR improvement. If you look OSR improvement also, if you L is 1, say L is 1, just suppose that order is 1, still I able to improve my SAR ADC or flash ADC by improve the OSR. Okay. But that will be not maximized. It will be log value, right? You know, log value means very high value means you will be have a very low value, right? Suppose 2 to the power 6 or 10 to the power 6 log of that, how much will come? 6 into 2, 10 or 20, whatever that one you say 60, but not 2 to the power 10 to the power 6, right? Basically. So OSR improvement, this last term, OSR improvement also improve your SNR, but you have to order as to fixed up. So all together improve your high dynamic range or SNR improvement will be high. So you're able to get a high resolution. So who has given this term? One is the oversampling, and this order, whatever the quantization you were saying, that order of modulator, they are doing noise shaping. What is meaning by noise shaping? Aditya said, suppose I'm doing a noise because he said that there is a green color and there is a black color, there is a main signal, right? There is a quantization noise is there. So one thing in the loop, when you are applying the noise behaving as a high pass filter and the signal behaving as a low pass filter, that is the beauty of the sigma delta modulator. Sigma delta modulator such a develop that noise has been, he has shown the graph. So noise has been acting as a basically high pass and your signal is low pass nature of that one. So whatever, if you have a equivalent low pass filter is there in the term, so you can remove the whole noise outside your filter. Okay, so sigma delta level, whatever noise is there, you are trying to throw the noise on the higher frequency, and that's why you are basically removing the quantization noise further. So that's why you are getting a more beats on that. So what happening in that? Suppose if you see what is come actually, this is the 1-bit quantizer level representation. There is no beat. Actually, this 1010 stream. There is no level, no nothing is there. 1010. This will become on that. Okay. So this is your beat. Don't consider this is equivalently say whatever binary representation. You say 7. 7 means 111. No, nothing. It is a different presentation in the delta. And delta sigma level also calculation. Suppose what is the calculation? You do addition, subtraction, or multiplication. There is a different norm. Okay, whenever you take the delta sigma beat, when you want to calculate, right, arithmetic calculation, you know, like you want to adder, you know, subtractor, you know, multiplier, that will be completely different story. It is not like a digital SAR ADC. You have a digital bit, you design a half adder, full adder circuit. There is some similarities there, but there is a different thing. Then one more thing was there, what Aditya said, that there is a oversampling doing. Oversampling means each of the point I'm getting lot of bits, like basically. So after that, they do decimation, because those many oversampling I don't need as a bit stream equivalently. Okay, I need a lesser sample. They do a decimation. So not only the circuits require analog concept, you need a decimation concept also to make the circuit to be digital centric. So digital part also involved in the Sigma Delta ADC. So this is the whole story of the Sigma Delta. And Aditya, what is the practical challenge basically? How you will be do that high order Sigma Delta? What is the integrator you design? How will we switch the cap? All you come, Aditya also will be with us. They will be help you to build that kind of in the MATLAB to synthesize a Sigma Delta ADC. And if you come in the, if somebody has interest pipeline, will be give a hands-on, how will we design a pipeline? So our IIT Hyderabad target is this one on that. Okay. So I want to stop, I think. Okay.
Okay. Thank you so much, sir. I would like to take few questions also. The students are asking what is the duration of this course. The duration of this program is 2 months, including a live lectures and doubt clearing sessions. And there will be 2 sessions per week. And the duration of each session will be 90 minutes, followed by live doubt solving Q&A. The live lecture are planned every week at 6 p.m. to 8 p.m. on Wednesday and 11 a.m. to 1 p.m. on Saturday. So all sessions are recorded also. If anyone is unable to attend the live lecture, they can go through the recorded lecture anytime. And another question I got, the course mode is online or offline? Of course, course mode is online, but if you choose a boot camp, so that is offline. And another question is, one of the student asked that I can't afford it. So we have a no cost EMI option also. So they can take that option also. And one student is asking, can you please upload the PowerPoint presentation somewhere online? So Aditya already pasted a link here on the chat box. You can take that link and check their presentation also. And beside this, we have a complete recording of this session on the Jobinar page. In future, in few days, we will upload that recording. So there also you can check this lecture again. And another question I have, ma'am, is this course available for free of cost or paid? So see, the course is paid. I'll already explain you the amount. And we have a discounts also on the course, 10% discount on the certificate course or 6% discount on the bundle product. It means that certificate course plus boot camp. So with this, Aditya, can you please continue with your remaining slides?
All the circuits being discussed here, like the gate bootstrap switch and the strong arm latch, usually like in lectures you'll see they take like half an hour or like an hour to discuss. The gate bootstrap switch, the switch itself takes like 1.5 hours to discuss. And like the discussion is required. You need to know like why each and every transistor is there in order to debug it later when it doesn't work. So yeah, here rather than speed, like for the overall thing, we need to have more like in-depth knowledge. We need to know things, need to understand why they're working or why, so that you would know why they're not working in some specific case.
Keshav is asking, what is the benefit for instrumentation engineering students related to this course?
I think whatever Aditya today giving Sigma Delta modulator, you look your instrumental course, any instrumentation amplifier which is you are using on that, this is the heart of the amplifier. So instrumentation amplifier people, if you analog is the heart of their thing and that. So they are very benefit through this course. In that. Whatever chip they are seeing for a outside, they will to implement by their side in that.
ठीक है sir. So second point is sir, another question is, which is in more demand, in a market, digital or analog VLSI?
I define this way, as I said, mixed signal is the more versatile application. Okay, so if you know mixed signal, then you will get a digital, you get an analog.
Mismatch is what prevents us from using like SAR or something for like really high resolution things. But still, that issue does arise here in Sigma Delta as well. So in our design itself, we had capacitor which was like 1400 femtofarad, and if it varied just by like 1.4 femtofarad, like there's like 9 capacitors, if like even one of them was like 1.4 femtofarad higher or lower than expected, then SNDR would go from 100 to 78. And that means like the noise and the distortion that is present in the circuit is like 10 times more than expected. So how do we actually solve this? Because there's no way that we can even achieve like 1.4 femtofarad plus minus. Like 1% is like a really good number. So we have to do dynamic element matching. Let's say our DAC needs to output some one element it needs to provide. It doesn't use the same element each time. It uses the element. Next time it needs to use the element, it uses some other element. It cycles through all of them so that the whatever mismatch is there, it gets averaged out. And anyways, we are doing oversampling. So whatever errors come due to this, they're at a higher frequency. So that is the reason for dynamic element matching. Without that, you can't achieve like greater than like 78 or something or 80. So that also becomes a limiting aspect. FIA, this is a high level concept. This is a pretty new circuit. I won't cover this now, but people can look at this document, that JSSC paper. This is usually how the spectrum will look. This high frequency noise you can observe, but we just cancel it out using a decimation filter. So it doesn't really matter to us. So that's the entire thing. Thank you for your time. I've listed 2 playlists here. The first playlist, I believe like anyone who wants to do anything in Delta Sigma, they can spend like, I don't know, 10-15 hours to watch the first playlist. It's by Dr. Ashwin from IIT Kanpur. He has really good lectures on each and every aspect of it. And the second lecture is from Dr. Shanti Pawan, IIT Madras. That is like about 60-70 hours. And that is really detailed. He has like an entire 1000-page book on it. So you can go to that level. Yeah, this topic itself is very in-depth. But if you want to start, you can start with the first playlist and just focus on the Delta Sigma. That should be fine. And that's the end of the presentation.
This we have come to the end of the session. In case if you all have any more doubts, any more questions, you all can always reach out to us info.tcsionhub@tcs.com. And thank you audience for your active participation. Thank you once again for your time and presence. So I, Shruti Khurana, signing off. Have a pleasant evening.
Yes, bye.